Hey guys, Greg here. Let's solve balanced binary tree, leetcode number 110. So we're given a binary tree and we need to determine if it is height balanced. And what that means is, well, a height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. Now that sounds kind of confusing, so let me show you an example. Okay, if we were given this tree, this actually is height balanced. So we'd want to return true for this. Now, if it is height balanced, it means that its right height, which happens to be 1 here, and its left height, which is 2. The difference between its two heights, 2 minus 1, and we actually want the absolute value of that because we just care about the distance between those two things. That is equal to 1, and so that is at most 1. So as the definition said, as long as it's less than or equal to 1, then that means it's good to go. Okay, but we need to check more than that. We're not just talking about the root here. We need to make sure it's balanced everywhere. So the root might be balanced, but there might be an issue elsewhere. Let's check the other nodes. Well, if we look at this node, well, its left height is 1, its right height is also 1. The difference between those things is just 0, and that is also less than or equal to 1, so that is okay. If we were to look at any of these three nodes, well, all of their left and right heights are both 0, so all of those are going to be zeros. The difference between 0 and 0 is just 0, so all of those are balanced as well. So because all of these different nodes, all of the nodes in the tree are balanced, therefore the whole answer would be true. If we had a tree that looked like this, well, now if we look at the root here, the root would have a right height of 3 and the left height would be 4. So it's comparing 4 to 3. The difference between that is just 1. And so there's no problem in the root here. And there's actually no problem here either. That's comparing 1 to 2. That would be fine. But there is a problem if you're talking about this tree. So if you're rooted in this tree right here, if you're rooted in this, well, its left height is 1. Its right height is 3. And so just for this node here, the difference would be 2, which again is bigger than 1. And therefore, since there is a problem somewhere in the tree, there is a problem overall. And so our total answer would be false. So we'll assume that it's balanced through this global variable, and we'll do our DFS here. And if we kind of ever find that, oh, here, there is actually an issue here, well, we would change this to be false here. And so that way, once we kind of came back from our DFS and we were done our helper function, after we are escaping this, we could check if we're balanced or not. If we ever turn it to false, our total answer should be false because there was a problem somewhere. Otherwise, if there wasn't an issue, well, then it just should be true like it was before. And so we can just kind of return the value of this global. Okay, so let's actually just assume that we are balanced, and you actually want this as the list of true. If you don't know why, I explained this thoroughly in the diameter of a binary tree video, but in general, if you don't know why, I assume that we are balanced, and you actually want this as the list of true. If you don't know why, I explained this thoroughly in the diameter of a binary tree video, but in general, you would want this to be a list when you're talking about a global variable, instead of like a local variable to the recursive function. Okay, then we're going to write a recursive helper function that's going to basically return the height of a tree. So it's going to return the height of a root. Now, if we don't have the root, well, then we want to return 0 because a non-root shouldn't contribute to the height. Otherwise, we need to get the left height is equal to the height on the root dot left. And we also need to get the right height, which is equal to the height of the root dot right. And now we can immediately say, hey, if the absolute value of the left height minus the right height, if that is ever bigger than 1, well, then that means there is a problem. And if there is a problem, we want to set our global, so you need to do balanced at 0, is equal to false. So now that we've done this, if there was a problem anywhere, that means there is a problem overall, and our complete function here, this function should return false. So we set that to be false, and now there is always a problem. Now, if that is actually the case, we really don't care about the height of our function anymore. And so I'm just going to return 0, because if you've set the fact that there is an issue, well, then we know at some point we're going to end up returning false. And so we really don't care if our height thing is actually working at this point. It's already going to return false. So we'll just return the value of 0 in that case. Now, otherwise, if we haven't ran into an issue, well, then we just want our function to return the height. The height of our current node is going to be 1 plus the max of the left height and the right height. Okay, so this function is called height because it's returning the height of a root. That way you can get the left height and the right height, and you can measure to see if our current node is balanced. If it's not balanced, we ran into a global issue here, and so we set that. Otherwise, we just want this function to return the height so that maybe somewhere else in the tree you could find if there's an issue. Okay, so from there, we just want to call height on the original root that we were given, and then we want to return our global, so balanced at 0. Okay, now there's actually a slight optimization that we could do here. Now notice that if we do call this on the root, well, it's going to go down left here, and it's going to do a DFS going all the way left. Now you could find an issue anywhere in the left there. If you ever found an issue in the left, if at this point, if just after we've gone down the left, well, if we know that the balanced at 0 is false, so if that is actually false, well, we know we want to return false, and we just want to escape here. And so we will actually just return, again, we'll say the bogus value of 0, because we're saying if you found a problem in the left, we just want to get out of here as fast as possible and not go down to the right, because an issue's already been found. Okay, so the time and space complexity of this solution, well, the time complexity is just going to be big O of n here because we are visiting every single node in the tree and we are doing constant work here. Okay, all of these nodes here, we're not really doing anything crazy per node. And so it's just going to be O of n because we visit all the nodes. And the space complexity, this is ultimately a
Hey everyone, so we can return
Hey guys, Greg here.
Hey everyone, welcome.
Hey guys, Greg here. Let's solve diameter of binary tree, leetcode. Number 543. So we are given the root of a binary tree, and we want to return the length of the diameter of that tree. The diameter of a binary tree is the length of the longest path between any two nodes in the tree, and this path may or may not pass through the root. And the length of a path between two nodes is represented by the number of edges between them. So it's the most amount of edges that we can get throughout the tree in a consecutive path. Okay, so if we were given this tree as input, well, the diameter is the length of the longest path and the number of edges of it. So it's 1 this way, 2 over here. We don't want to go down here because we can actually go over here and get another 1. So we can get from this node all the way over to this node if we take this path, which is made up of 4 edges. So in this example, the diameter of the tree we'd want to return is 4. Now in this example, we can see the diameter actually another 1 here, the path between them. So it's the most amount of tree as input, well, the diameter is the length of the longest path and the number of edges of it. So it's 1 this way, 2 over here. We don't want to go down here because we can actually go over here and get another 1. So we can get from this node all the way over to this node if we take this path, which is made up of 4 edges. So in this example, the diameter of the tree we'd want to return is 4. Now in this example, we can see the diameter actually is passing through the root of the tree. Okay, it's passing through this node. That doesn't actually have to be the case. Basically, if we were to extend this a little bit, we'll say add a 7 over here and 8 over here. We'll add some over here. And if we just extend this one more here, so we'll extend this a little bit, we'll give this a 10 and we'll give over here an 11. Well, notice now that if you go through the root, the original root we were given, we're stuck with just 1 from the right side, and then you can go all the way down to the bottom. So that would give, we could either go over here or we could go over here. Either way, you're going to get 1 from here, 2, 3, 4, 5. Okay, so you're going to get a diameter of 5 if you use the root. But if we don't use the root and we actually use this thing's diameter, well, then we actually have 1, 2, 3 up to it, 4, 5, 6. Okay, so you get a better diameter by not using the root node as part of it. So as the question says, the diameter of the whole tree, the diameter is the longest path throughout the tree between any 2 nodes. And the diameter is the longest path throughout the tree between any 2 nodes. And it happens to not use the root. It actually uses this node as the root. So it's basically, curving over at that point. So we can think about it as like every single node, they actually each have a diameter. This thing, if you were to treat this as the root, well, this thing has a diameter of 0 because it has no left and it has no right. We're saying we can't go back up because you're saying like this thing's diameter in total, well, it is actually just, 0. It's nothing. And so if you were to look at this thing's diameter, well, it is going to give 1 from over here, and we can also get 4 from over here. So if you're to root with this tree, well, then its diameter is 5. And if you were to root with this tree, as we saw, well, its diameter is 1, 2, 3, 4, 5, 6. Okay, so its diameter, if you root here, its diameter is 6. And what we want in the question is the biggest diameter that we can find here. Even though, of course, we're given this as the root, we don't necessarily want its, diameter because that's 5. We want in the tree the longest path that we can get between any 2 nodes. That is going to be rooted right here, and so that is going to give a diameter of 6. So we want to look at every single node in here and get each of their diameters. And we also want to keep track of basically a max diameter where we'll have this as like a global variable, say it's equal to 0 so far. And if we were to look at, say, this node right here, well, it would have a diameter of 0 because it has no left it has no right, and so really that's just 0. That doesn't find a better max diameter. But then if we were to look at this node right here, well, it has a left of 1. We have 1 edge going left here. We have nothing going right. And so this thing's diameter, well, we could find out that its diameter is 1, and then we'd update that by saying, okay, well, we found a better diameter than 0. We found a diameter of 1. Can we do better? Well, if we look at this thing's diameter, it's got 1 from the right, so it's got 1 there. It's actually got 2 from the left, and so it's actually going to be 2 plus 1, which is equal to 3. We can see a path of 3 right here. And so we say, okay, we actually found a better one. We found a 3. So we're going to keep this pattern up, and we're going to do a depth first search. So here, we're going to initialize our max diameter at 0, and we'll look at the diameter of each of the nodes. And we'll do that through a depth first search. So basically, we're going to keep going left, keep going left, keep going left, keep going left. And we're really going to look at this thing's diameter first. Any node's diameter is equal to the height of the left, so basically the height of its left subtree, plus the height of its right subtree. not the diameter of the left and the diameter of the right, the height of the left plus the height of the right. Why is that true? Well, let's look at this node, because if we do a DFS going left, that's what we're going to see first. Its left height is going to be 0, and its right height will be 0. And so its diameter is simply the left height plus the right height, which is 0. So this thing has a diameter of 0. We'll see if that updates our maximum. It doesn't happen to. But if we make this function return the height, so our DFS will return the height, well, then we go over here, and this thing will know that its left height is 1. And this thing, its right height is going to be 0. Okay, now it can check its diameter. And so its diameter is just the left height plus the right height. And so this thing's diameter is 1. We can see that. It's just this one edge here. Okay, so that actually beats our maximum. And so this thing will have a diameter of 1. This thing's height is going to be, well, if you remember the height formula, height is equal to 1 plus the max of the height of the left plus the height of the right here. Okay, that's how you get the height. And so this thing is going to be 1 plus the max of the left and the right. That is 1 plus 1. And so this thing's height is 2. So now this thing knows that its left height is 2. This thing's right height is 1. And so this thing is going to have a diameter of the left height plus the right height, which is 3. Okay, so if it has a diameter of 3, that actually updates our maximum. Well, its height is 1 plus the max of the left and the right. That is 1 plus 2. And so this thing knows that its left height is 3. And I'm not going to do all the calculations, but for this guy, it would actually figure out that its right height is 1, 2, 3. And so this thing's right height is 3. That means its diameter would actually be 6. And so it would get that this is a 6, and that would update our maximum. Okay, so that's the maximum diameter we've seen so far. And just to trace it out, it would be 1, 2, 3, 4, 5, 6. Okay, well, this thing's height, its height would be 1 plus the max of the left and the right. And so this is going to be 4. This thing over here, this height is going to be 1. And so this thing's diameter is going to be 4 plus 1, which is 5. That does not create a bigger maximum, as we saw. And then our total general function would return the max diameter, which happens to be 6. So let's write the code. Okay, so we want to set largest diameter equal to a global here. And so that we will set to be 0 for now. And this is actually going to change to something at the end, but I'm purposely making this wrong to kind of explain something at the very end. It's a very weird Python topic. Now we're going to make a helper function, which is called height. So it just returns the height of any root. Okay, so how do we do that? Well, if the root is none, well, then that shouldn't contribute to the height. And so that thing's height is 0. Otherwise, we need to get the left height is equal to the height on the root dot left. And we also need to get the right height, which is equal to the height on the root dot right. And we'll make this return the height. And so it will be return 1 for itself plus the max of the left height and the right height. So this function as is would return the height of any node. Now in here, we can actually get the current diameter because we have the left height and the right height. We can get that the current diameter is equal to the left height plus the right height. And now that is the current diameter. It may or may not be the biggest that we've seen because this is just a diameter of, whatever root we happen to be calling this on. So we want to set largest diameter equal to the maximum of the largest diameter itself and the current diameter. Okay, so you'll see this type of pattern a lot. The largest diameter is going to be the max of itself and the current diameter. So if diameter is bigger, it'll be set to that. Otherwise, it's just going to keep staying as it is. Okay, and then from here, all we'd have to do is just call height on the root because that's automatically going to do a DFS or a depth first search through this whole thing, and it's going to update the largest diameter, and then we could just return the largest diameter. Please keep watching the video because this is actually wrong as is. This is not going to work. Because of a weird and possibly unexpected error, cannot access local variable largest diameter when it is not associated with the value. Okay, so basically what's happening here, and I'll just show you how to fix it very quickly and then explain it, is the way to fix this would be to put this as a list of one number. And from there, you'd have to adjust a couple things. Largest diameter at 0 is equal to the max of largest diameter at 0 and diameter. And then you'd also want to return this. So that is actually what allows this to work. Now it is working great. Okay, so the reason that we needed to make this a list and we no longer get that weird unaccessible error is because taking it back to a second what it just was. Well, as it is here, in this statement right here, this is a problem. This is saying that a local variable to this call of the function is largest diameter is this stuff. Now I'm saying local variable because it is local to this call of the function, as in, as you're going through a depth first search on these nodes here, it is actually keeping the call stack open. It will make a recursive call stack. And so each of these nodes would actually have a largest diameter, just like each of them would have a left height, a right height, and their own diameter. You don't want largest diameter to be local to this particular call of this function or whichever root you're talking about. We just have one largest diameter. And so we want to particularly say that this global variable across all calls of this root, remember that's the whole point, is to try and find the largest diameter, so that here you're not saying a local variable is equal to this. You are referring directly to this global variable, and that particular spot of memory that is going to get updated to this. So it's a slight change, but just note that this syntax of sub-0 setting this to be something that sets a particular memory spot, and this is saying this local variable is now equal to that. So they are different things. You would want to make that a list. Okay, so let's talk about the time and space complexity of this function. Well, time is just going to be big O of n, where n is the number of nodes in the tree. We're basically just doing a bunch of constant stuff for every single node in the tree. We're calculating its left and right height, the diameter, and the largest diameter. All of this stuff, it is just constant operations per call of the function. Per node in this tree is just a bunch of constant stuff. We're visiting every part, and so that is O of n. And the space complexity, this is actually doing a depth first search here. It is going down to the bottom and collecting it back upwards. And so you're keeping that call stack open. And so this is actually going to be big O of h, where h is the number of nodes in the tree. It is going to keep the height of the call stack open. I hope this was helpful, guys. Drop a like if